the first session. So now the eminent speaker Suman Gowda NC with us today. So now let me introduce about him. So Suman Gowda NC is a senior application manager in additive manufacturing from Philips Mission Tools and India Private Limited. Mr. Suman Gowda holds BTech Mechanical Engineering and master's degree in printing technologies from University of Germany. And he has a vast experience in additive manufacturing field, has worked closely with several automotive and aerospace customers to implement additive technologies successfully in their organization. And he has also successful in guiding several education institutes in the field of additive manufacturing. He has been a part of numerical projects related to automation of assembly lines and tool development for faster production and UAV and drone technologies and drone development and defense and aerospace projects, and also automotive and new product development along with the materials analysis. Currently, he is working as an application manager in Philips Mission Tools India Private Limited. His expertise in additive manufacturing as a successful implemented in several manufacturing facilities and education institutes as well as research centers and R&D centers. With increased production and reduce the cost per part, the additive manufacturing technologies are one to be implemented for every organization. So this is a very great profile, sir. So now the Suman Gowda with us. So sir, now I'm handing to you. So you can continue the session, sir.
Thank you. Thank you very much. So hello everyone.
Sir, your voice is very low, sir.
Okay. Yeah. Is it clear now?
Yes.
Okay. Hello everyone. Very good afternoon. So thank you for having me over for this session. So hope last 4 days, so the sessions have been truly encouraging. So today's my session will be dealing mostly on the composite section of the materials and the printers and a few of the composite plus resin grade printers as well. So considering your previous schedules of all the metal processes and technologies, what you have gone through in last couple of days. So this will be regarding the composites. So let me share my screen. Just give me a minute. I hope my screen is well. Okay. So we in Philips Machine Tools, we represent numerous varieties of products. Additive is
Sir, your voice is low, sir.
just okay. Let me turn off my video as I'm starting the session. Okay. So I hope now the network should be clear. Can you hear me
Yes, sir.
now?
Yes, sir. Clear, sir.
Well
Yes,
now?
yes.
Okay, fine. Thank you. So, okay. So in Philips Machine Tools, we deal with numerous products from milling to turning, grinding, and additive is one of our vertical which we started around 6 years back, and now we have close to around 8 different solutions in additive. So where we cater into applications which are of all the varieties of materials, from the metal grades material to the composites to the resin and to the powder, and then we also have a research oriented materials which can be used for direct metal deposition, and we also do have the process of laser melting the wire and the metal powders as well. So as I mentioned in the beginning, in today's session we will concentrate on the composite grade printing, and we will also have a look at the liquid based printers as well. So coming to the printers portfolio, so as you might have seen in the last couple of days, so there are a lot of varieties of technologies in 3D printing alone, which can give you a different kind of solution. Some solutions talks about printing parts for prototyping applications. Some solutions talks about printing parts for end use or one-time use applications, and some can also be used for mass production, where whenever the tooling cost and the printing cost can be compensated. So now we are in such an era where we usually try to bring 3D printing to almost all the vertical and almost all the applications where we can. So looking at that, composite-based printers is one of the major highlight. When I say highlight, this is a process where you can print parts which are as strong as aluminum. But imagine the printer that you use for printing it is a simple desktop printer. So you just place it on your tabletop and you print a part, and that particular part is as strong as aluminum. So that's where the major strength of the composite based printers and material comes in. So we will have a thorough look at that particular technology. So Markforged is an US-based company who actually have developed the concept of printing with continuous fibers. When I say continuous fibers, so you might have seen a lot of plastic wires which are having few amounts of composites or few amounts of wood grains or few amount of other particles infused in it. So that will give you an enhanced strength. So the strength with what you get from the composites or the powders mixed in your raw material wire will be, let's say, around 2 times. Whereas in case when we use a continuous fiber, the kind of strength what we can achieve is 20 times to that when compared to the when we compare it to a ABS grade material. So So when we look into that kind of applications, so we always need to see, okay, what's the strength to weight ratio that we get? So we have been very successful in implementing this particular carbon fiber parts in lot of applications where aluminum was previously used. It might be from an end use gripper applications or applications which are an end use part of drones or applications which needs to hold a weight of around 100 to 500 kg of load. So all these things can be easily done by these Markforged grade printers. And with Markforged, we give a complete clear solution, which talks about the printers, these softwares, and also the materials that we provide. As I said, we have our own proprietary materials of fiber grades. So we have got lot of institutes and students who have been doing research and R&D. The research is, it can start with a simple concept of even printing a tensile or a dog bone sample. But imagine you can get one single dog bone sample printed with almost 20 different variations. And just doing a study on that alone is a complete topic for the master thesis. And then similarly, we have got 4 different kind of fiber materials. We have got carbon fiber, we have got glass fiber, we have even got Kevlar. We have also got something called as high temperature fiber. So each fibers behaves differently under different environmental conditions, under different load applied conditions. And when we talk about these particular materials, so these materials are not melted. We are just kind of ironing these particular fibers on top of a plastic part. So just to give you a concept of how the technology works, I'm sure all of you would have seen an FDM printer printing. So the concept is the same as an FDM printing, and this has got 2 nozzles. And suppose if you have used printers with 2 nozzles, you might have seen one nozzle is for the plastic and the second nozzle is for the support. Whereas in our Markforged, the first nozzle prints both the model and support, and the second nozzle is dedicated only for the printing of fiber. So the fiber acts as a kind of an main strength for it's, you can imagine a pillar of our houses or pillar of any buildings. So the main strength for the pillars are the iron bars, right? And we kind of use the cement and the concrete just to surround around it to make sure that the iron rods are not exposed to the external environment. So we follow almost a similar concept. We kind of have a boundary built using a regular plastic, and then inside that boundary, we have got our continuous fibers which will be deposited. And the plastic what we use for regular printing is also an composite grade material called as onyx. So these are the varieties of printers what we provide for printing of the materials. We have got different size ranges for printing. This is the tabletop printer which can be placed at on any particular table which weighs less than 20 kg. Then we have got a slightly bigger version which is around 330 by 270. Then we have got the mid range which is 375 by 300, and then the bigger one which is of 500 mm. It's just to give you an idea of different varieties of sizes that the parts or can be printed. Here's a small example of how the printing will happen. As I said, it's as simple as an FDM printer printing the part. So the part keeps on printing layer upon layer. After every layer is printed, the bed comes down around 100 microns or 200 microns based on the settings we have used, and then the second layer gets deposited. But the best part is the nozzle one prints this entire black material what you see. The nozzle 2 is actually printing the fiber. And that particular fiber is kind of pressed on top of this plastic part. And then because of the heat, the fiber gets bonded with the plastic. And then as we build it layer upon layer, the part strength increases by 10 to 20 times. And we always have an option to select the amount of fiber that we are going to deposit. We can deposit fibers which are complete 100% to the part, or we can deposit fibers which are hardly around 10 layers in my 100 layers part. Or if my part is of 100 mm, I can have fibers in the bottom 5 mm and in the top 5 mm. So it completely depends upon me how I want to add the fiber. So now moving to the next step, which is the applications of this. So the reason why I'm talking about the applications are because whenever we look into an FDM grade machine, we always start with a prototyping, we always start with a fitment. But imagine an FDM grade printer where we talk about applications which are similar to that of metals. So whenever you consider a metal grade printer, which are worth around like 1 to 2 crores or even more, we talk about manufacturing of tools, manufacturing of grippers, manufacturing of dies. So those are the same applications what we talk when we are talking about a composite based 3D printer. Because the composite based 3D printer gives us that advantage which none of the plastic printers can provide. And at the same time, when necessary, the same printer can also be used for printing the regular plastics as well. Because we also have an option of printing with the regular PLA and the rubber grade material in the same printer. But the main USP of this printer is printing with the continuous fiber, which gives us the extreme strength to the part. So if you can see, the graph in the left shows ABS having a tensile strength of 32 and our onyx, our main proprietary material, having the tensile of 71 and aluminum 310. But the carbon fiber, the continuous carbon fiber, what we use for printing, it alone gives us 800, which is double to the strength of an aluminum. Yes, we hardly utilize 100% of the fiber strength, but even if you are able to utilize 50% of the fiber strength when we deposit in the parts, we are still getting parts which are similar to or superior to the strength of an aluminum. So we do not even, we have got a lot of customers who have started their production even without a CNC machine. So they are printing all the kind of clamps, holding grippers, tools using a small FDM-based composite 3D printer, which can give them parts as strong as aluminum. We have got drone customers who are using around 10 to 20 of such printers as a farm so that they can directly print an end-use component of drones and it can be used for them. So overall, we are talking about transition from an regular machined aluminum or a casted aluminum to a 3D printed composite parts, which can give us the equivalent strength. So this is kind of an industry trend or the kind of industry adaptation to the 3D printing, I would say. You might have seen maybe the similar kind of slides in your previous sessions as well. So if you can see 3D printing, which is almost a 30-year-old technology, because of the patents, the first 15 years was very limited and it was not available to everyone. Later on, when the 3D printing became available to everyone, everybody started to try out with the concept, but it was not as successful. Few of the industries like aerospace and medical really explored the application of additive. And because the components or the number of quantities in aerospace and medicals are limited when we are comparing it with an automotive industries. Because in automotive industries, we talk about lakhs of components, whereas in case of medical or aerospace, we talk in numbers like tens or hundreds. So that was one of the reasons why aerospace and medical were able to explore more on this additive platform. And now with the automotive industries, we have focused our intention for the tooling industry, where we do not require lakhs of tools. We will be requiring only few thousands or sometimes few hundreds or sometimes maybe even one quantity. But the way that particular tool can be manufactured is something where the entire 3D revolution is happening around. And coming to that fact, we have got numerous varieties of approach which we can take. Metal being the front runner for a lot of applications when we are talking about the conformal cooling or when we are talking about applications which requires hybrid process. And the composites also give a huge advantage when we consider using the composite based materials to producing of an end use tool parts. So here's is this was just to showcase the product, and these are the different materials. So in this, the first four materials are, I would say, as the individual materials, which are regular plastic grade materials, and the last five are the fiber grade materials. So when we are talking about the printing option, we are going to combine the regular printing along with the fiber part. If you look at the last part, so the black part is actually the plastic and the yellow is the continuous fiber. So when we look at a component, it looks like a regular plastic part, but the internal filling would have happened with the fibers. So that is what giving the main strength to the part. Yes, there are few design guidelines that needs to be followed. Like for example, you need to have a minimum thickness for getting the fiber to be deposited, and what should be the minimum height for the fiber deposition to happen, and what should be the minimum area square. We have got a complete data list for that if you want to explore more into that kind of options. But looking at the deposition in the right side, last all the five images, if you can see. So we are talking about depositing of the fiber inside of a plastic component, and it happens layer by layer. So we have got complete control over which layer the deposition should happen, which layer the fiber deposition should not happen, and what is the kind of deposition that should happen. For example, we make the deposition in such a way that we give an option to deposit parts which are only in the boundary, or we have the option to deposit fiber for 100% of my part, depending upon my end application. For example, my end application is to withstand a weight of just 20 kg. I can just use fibers only in the boundary. If my end application is to withstand a weight of more than 100 kg, then I might have to use the fibers complete body of for the complete body. But the best thing, we even have a software which tells us what's the percentage of fiber that is required for the load that is being applied. Like for example, if you are going to, let's consider, okay, just for example, I'll just consider the same part. So consider a turbine housing where you are going to mount the turbine housing and you're going to apply a load of, let's say, around just 10 kg, then a regular plastic of our onyx is sufficient enough for the job. But if the weight is of 100 kg, then we also get to ask the software. So this is the kind of my application. This is where I'm going to apply the load. What should be the fiber reinforcement for this part? So the fiber itself tells us what's the kind of fiber that is required. Yes, you can get to know more about it as you work on it. So once you have started to work on this, so you can take a judgment and say that, okay, this will require fiber of around 20%, or this will require fibers in the boundary that is sufficient enough. But if you are not able to take that particular judgment, the software itself will tell you that what needs to be done, so that you do not have to make your trial on getting to the best settings for the print. It happens, the print, the software gives the solution to us. So here's few examples of parts printed with regular plastics. Even though it's a regular plastic, it is still superior than the strength of ABS, and it can withstand numerous chemicals, and it can withstand more than 150 degrees of temperature. So that gives it a huge advantage for to be used for a lot of end application needs. So this is a small graph comparing to the ABS and nylon grade to the onyx grade material. And when we talk about the continuous composites or fibers, so there's a huge difference when we add a small amount of fibers and mix it along with our plastic components and draw a wire. So this is what you get. The first image is actually the, let's say, a powdered carbon fiber. And when we are going to get our regular onyx plastic wire, so that is a combination of nylon plus this amount of chopped fibers. So this will give me strength which is only 2 times to that of a plastic. But the main strength comes when I utilize the continuous fibers. And this is how the printing would happen of a continuous fiber. As you can see, the black is deposited on the boundary, whereas the yellow, which is the continuous Kevlar fiber, is being deposited on the entire part as per my end application. And because of this fiber, I am going to get an unique strength. Or in the image, if you can see, it's the software image. If you are able to see the blue line, so this is the fiber path. So in this part, we have decided to give the fiber only in the boundary, whereas the infill geometry is still around 30%. So what happens is this part is now 50% lightweight than the existing aluminum part, but it is still giving the same strength. I can even increase the strength of the fiber by increasing the fiber lines so that the strength becomes more superior based on my requirement. So the advantage what I get over this is the strength to weight ratio is completely under our control. So we don't have to depend upon just the density of the part. So I can still go lightweight even than this, but still achieve the same strength that is required for my end use. So here's the components which would look like once we deposit the material. So as you can see, we have got the fiber deposited only in the boundaries. So this kind of deposition, we call it as external and internal boundary, so that it has covered the fiber with the external boundary, and also the circles also are being covered, because there is a point that I might have to do the clamping, and then that particular area need to be strong enough to withstand the clamping force. So I've given fibers on even the circles. So it depends upon my end applications overall. So it's a free software actually called as eiger.io, eiger.io. So you can just go to Chrome, just go to this, it's a cloud operated one, go to eiger.io, just log in yourself, and then you can upload the files, and then you can start working on lot of varieties. We even got a tutorial videos that you can also get as soon as you log in, so that it can give you a complete overview of how the fibers are being deposited in the particular part. So you get almost more than or around 50 to 60% of the access of the software for free, so that you can get hold of the complete operation of this, so that you can see how the fibers are being deposited, how the fibers can be changed, and what's the kind of, suppose if you're looking into some kind of research activities, you can also see what kind of research can be done on particular this topic. And just to show you a comparison, so if you can see the regular plastics, we are looking at below 100, whereas when we combine it with this kind of fibers, we talk about strength of 200 to even which goes up to 500. So there's a huge deviation when it comes to whenever we have started to use the fiber. So now you are using a fiber of, let's say, Kevlar, and then you know what's the kind of elongation that you can get. So now you can even cross verify at what particular settings I'm going to get this kind of elongation. Obviously, it will not be true for all the settings. So you can just make that particular comparison, and then it becomes its own topic. So these are the kind of things that we are actually doing, working out with a lot of institutes. So here is a small example of a small chain link that was printed using an onyx plus carbon fiber combination, and you can see the kind of strength that this particular small part can withstand. So as we saw, the small chain link was able to stand around 22,000 pounds. So which in reality is like almost as similar to lifting an cement truck. Yes, but if needed, I can even lift it out, lift even such a huge weight. But the important point over here is only works when we are using the load in the same angle. If I change the angle of my load, maybe it will not even stand 10% of the load, right? So that's where we talk about design for additive manufacturing. And with the Markforged, we also say design for your part or design for your printer. Because when we exactly know that this is what I need to do, or this is what this part wants me to do, I get a complete advantage of this particular aspect. So that's the reason, one of the reason why the drone companies have been able to utilize this composite based printer to its maximum potential. Because even though they know that this particular part will not able to withstand around 100 kgs in when the load is when there's an impact load, but for them the main application is if it's just an holding clamp, and if this particular part can do the job of a holding clamp, it's more than sufficient for them. So that's how we usually do about 3D printing for the exact materials. So as you can see, we can print parts which can be used for end use tooling applications, which are a very high complex gripper parts, or it can also be used for a maintenance part. So this particular part in the middle, what you see, it's an end use maintenance tool, which is like 1/3 of the weight of an original component. So this will be uh, clamped to the industrial workers when they climb up towards the windmill. So as you know, they have to go almost close to around 200 to 300 feet high, and they have to make sure that they are not carrying huge amount of load. So this is 1/3 of the weight, and then it can do the same job. And also, as this is made out of plastics and not metal, they get lot of benefits when they are using this tool at such a huge heights rather than using metals. And the image on the right, you can see we have seen these particular parts being used in a lot of satellites, a lot of space exploration applications, such that the parts can be sent to space, and then once it returns from the space, it is still as good as a printed part. So there won't be any kind of deviation or blurriness or any kind of deflection that might have happened because of the extreme cold and hot. So as an experimental views, we can say this can withstand up to -80, and then in the positive side, it can go more than 150 to 200. So that it just gives us a huge advantage to work with very harsh environments. So it's a detailed video. So I hope the sound is okay when I play it.
Hi, my name is Daniel Azier. I'm a product marketing manager at Markforged. I'm going to walk you through the basics of our desktop series print.
Can anybody confirm? Are you able to hear the audio?
Sir, it's hearable, sir. It's
Okay, thank you.
completely okay, sir.
Okay, thank you, sir. I'm just playing it again.
Printer, which in my opinion is one of the most useful items you can put on your desk. Our desktop series consists of the Onyx 1, the Onyx Pro, and the Mark II. The product line offers incredible versatility in the applications you can address, and we do this in part by designing everything that goes into your printer. Our machines, materials, and our software were all designed to be tightly integrated into one platform we call the Digital Forge. What does this mean for our users? It means every part you upload, slice, and print is streamlined, simple, and optimized for incredible surface finish, accuracy, and mechanical properties. With other 3D printers out there, users may rely on one company for the hardware, another company for the software, and a third company for the materials. That introduces a lot of uncontrollable variables that can lead to some negative consequences like sketchy print quality and a lot of trial and error just to get your part to print the way you want it to. By contrast, Markforged makes the hardware, the software, and the materials to guarantee the highest quality. The Digital Forge offers a degree of harmony that just isn't achievable when you're trying to overcome the many variables introduced by combining a hodgepodge of systems. From day one, Markforged set out to address 3D printing differently by creating parts as strong as metal right on your desktop. In 2014, Markforged invented and patented carbon fiber reinforced 3D printing, or CFR, which allows users to make parts as strong as metal just at the click of a button. Our CFR technology is objectively awesome. It starts with two materials, a spool of base plastic and a spool of continuous carbon fiber. We first deposit a layer of plastic out of a hot nozzle and onto the print surface. After that, a second nozzle comes in and irons down continuous fibers right on top of that plastic layer. The printer builds the part layer by layer until it sends you an email letting you know that your print is complete. Right off of the printer, the part has properties comparable to aluminum, all at a fraction of the cost and weight of a CNC machined equivalent. The core element that ties these and all of our printers together is the software. It's called Eiger and it's free to use. The best part is you can access it from anywhere. You just navigate to eiger.io from a Google Chrome web browser and voila! I've literally kicked off prints in the back of an Uber. Seriously, for all you folks out there plugging in USBs to the back of your printer, back of an Uber. Eiger isn't just a slicer. It's an all-in-one part library, version management, and cloud collaboration tool. It will, of course, slice your part, meaning it converts your part into a set of instructions that's readable by our printers. But our slicer is optimized for our materials and printers, meaning there are fewer steps users need to take to get a great part out of the printer. While Eiger is super simple to use, it's also designed to give power users the unique ability to control where continuous fibers go in the part and how the part responds to mechanical stresses. All told, the Markforged Desktop Series printers empower you to address the widest variety of applications, from prototyping to end-use parts as strong as metal. Our printers offer a simple-to-use system that makes some of the best-looking parts you can build at your desk. We knew from the get-go that people were going to use this printer for incredible applications like high-strength tooling or even production parts. That's why the team sweat the details that are immediately evident when you pop the hood of this machine. The single-body aluminum chassis the printer rides on was deliberately engineered to resist the torque induced by the belt drive system. Why does this matter? The stiffer frame results in higher accuracy and improved surface finish, resulting in the high-quality parts that Markforged is known for. The precision extruder constantly pipes data back to the system to monitor the health of your print wirelessly. Even the coupling mechanism used to secure the print bed uses magnets and is repeatable to within 10 microns. That's nearly 7 times smaller than the thickness of a human hair. In addition to carbon fiber, we innovated printing with 3 other continuous fibers dedicated for specialty applications, including high temperature and high impact. We also recently announced our own version of PLA, which we call Precise PLA, offering our users a new, more cost-efficient means of validating designs before going into production. For more information about the full range of materials we offer on our desktop series and the capabilities of each printer, check out the website, which is linked below the video. The desktop series offers modern manufacturers the ability to validate concepts and implement designs with consistent high quality and repeatability you can trust. Have a part you want to print on our desktop series? Have an interesting application you need help with? Hit us up in the comments.
Okay, so I hope the video gave a lot of clarity about what I was mentioning about or what I was talking about. So if you still like to have a look at the live video or live printer, so you are welcome to like walk into our Bangalore, Pune or our Delhi facilities. So just let us know or just let the what is know, so you can plan your visit. So then you can even have a look at the printer, or if you would like any particular parts to be printed, so we can also work out on that, or we can, for your research oriented, we can see what's the best approach also that can be done. But overall, it's like you have an option where the research which you were doing out or carrying out with the metal. So now it's something that you can also do it with the composites, and then with the availability of 4 different composites and hundreds of settings of an FDM, lot of research activities can be performed. You can just Google around like the research activities being done on the Markforged printers or research activities being done on composites. So you can get to know a lot of new ideas that can be done. And then you can also do a lot of hybrid based researches that if you want. So overall, it's talking about varieties of options that opens up. So here's the fibers of 4 different like carbon fiber, glass fiber, high strength fiber, and Kevlar. So there is a slight amount of color difference for identification and chemical composition, but overall different fibers give different kind of results. So Okay, so before I play this video, so this is just to highlight how the printing will actually happen on the printer with the continuous fibers. So I will keep on explaining as the video plays. So now this is the base. Oh, sorry. Okay, so this is the base material, what we have the onyx, which is the black material, and then we deposit around 3 to 4 layers of this onyx just to make sure that we have got good amount of bottom surface. And then you can see we have started to deposit this blue line. So these blue lines are actually the fibers. So then as of now in the settings we have selected fiber only in the boundary, so we are depositing fibers in the boundaries of the part, and then the remaining section is being printed with the onyx. So if you can closely observe, so the external boundary is built with onyx. There are two nozzles. So the nozzle one prints the onyx material, whereas the nozzle two deposits the fiber material. And when it deposits the fiber material, we are not melting the fiber. We are just pressing the fiber on top of a plastic that we had printed as an initial base, so that the fiber gets bonded with the plastic. So the nozzle in the back, that's the job of printing with the plastics, and the nozzle in the front does the job of deposition of fiber. As you can see, it's a circular fiber material, and we are going to press it, and then it's going to turn into a rectangular shape. So this press, everything is pre-calculated from the software. We also have a small cutter which cuts the fiber just before the end spot, so that the fiber doesn't get stretched along once the printing is completed of that particular layer. So this is just to showcase the material when the printing happening. So if you look into the kind of an X-ray version view, the white material is actually the regular plastics, whereas the blue is the fiber material. So now it depends upon, like, now I'm going to get the same amount of fiber when the part is at a laid down position, but when the same part is in a standing orientation, the amount of fiber that is being deposited will be completely different. So you can go into the iger.io link and then upload the model, or just to start working on the model. So then you can start to realize the kind of difference that you will be getting. So once again, these are the 4 fibers that are being used.
Though it took more than 30 years to catch on, 3D printing is proving to be a cost-effective and cutting-edge way to produce a wide variety of parts. The machines use a largely automated workflow and can create complex geometries for no extra cost. As manufacturing continues to modernize, expect to see a lot more of 3D printing.
So this is just to show you an view. So the entire part would look like a regular black part, but when we look into the reality of the part would be having this kind of fibers inbuilt in it, which is actually providing the main strength to the component.
Howdy, I'm Charles Liu, application engineer at Markforged. Take a look at this lever. It's an onyx part, printed solid because you need it to be really strong. What if I told you you could cut print time in half, double the stiffness, and still maintain strength and cost? With the power of software and a little bit of continuous fiber, that's all possible. Let's dive in and I'll show you how. As engineers, we are always making trade-offs between quality, time.
So now we'll be discussing about our simulation option in our software, which is an add-on option. So this is just to showcase you that how using the simulation will give you a different perspective of how much fiber can give you how much load withstanding capacity, that particular option.
And cost. With 3D printed parts in particular, finding the right balance of settings to meet functional requirements can be difficult. We need the new part to be strong, quick to print, and cost effective. And in the past, we'd have to print and test multiple iterations to dial in the settings. It took a lot of time and a lot of materials just to get to a design that worked. Not anymore. Simulation from Markforged allows you to test your part virtually to see if it will be strong enough. You can then optimize the print parameters, including the placement of continuous carbon fiber reinforcement, all before you hit print for the first time. So let's use this lever as an example. You need it to hold a 100 Newton load with a factor of safety of at least 2. And it can't deflect more than 1 millimeter and needs to be as light as possible. How would you achieve that? Let's look at 3 different variants of the lever. The first was printed with default slicer settings. The second with a solid infill. The third part is optimized using simulation. We can see in Eiger that the first part took 3 hours and 32 minutes to print. It's not strong or stiff enough for us to use. The second print, with solid infill, took 6 hours and 19 minutes to print. It meets the factor of safety of 2, but has a maximum deflection of 1.8 millimeters. The third print, optimized using simulation, took 3 hours and 41 minutes to print. It meets the factor of safety of 2, cutting print time almost in half with the same required strength. With simulation, it took only a few minutes to simulate and optimize this part. Meanwhile, it takes 14 hours of printing just to arrive at the same conclusion. No more guessing how much or where to place fiber, or spending countless hours on print break cycles. Print the right part the first time. For more information on how simulation can save you time.
Okay, so this was just to showcase you the benefits or advantage. And yes, so once you have started to use this particular software after some working on it for some couple of times, you would have mastered the process of like which would be the best optimum. And it also makes a role when you would have done few studies or few trials on this particular printed parts. So you will get to know what is the best kind of settings for what kind of weight or what kind of load being applied. So you will get to know the varieties of aspects. So here are few applications like robot effectors or end arm tooling grippers, which were actually machined using an aluminum or stainless steel parts, which are now being replaced with the onyx plus the fiber combination parts. So you can see a lifting tool. This lifting tool can lift a weight to close to around 900 plus kgs, and a clamp bit, which is a regular simple clamp bit, can hold a weight of around 50 kg. The advantage over here is they are using the same clamp bit. They're just changing the grippers, and then it can be used for 5 different kind of parts holding. And the best thing is they can get all the 5 different kind of grippers printed overnight. So they don't have to allot a particular CNC machine for doing this job, or they do not have to consult a programmer for writing a program for doing the machining, or the designer do not have to go and wait in the production lab for getting these parts. He can just fire the print from his own designing seat, and then the parts gets printed. And as the printers are cloud operated, he can even fire the print from his home, and then he can get the part next day when he reaches the facility. So these are all the different advantages which the printer provides. So anyway, we have seen this video. So these are few of the replacement parts that we have personally done, like some of the parts like which were of aluminum, freshly machined part, which was easily replaced with an onyx plus fiber, or a casting part, or a sand casting application part, or a parts which were earlier they were using the casting process, which were replaced with the 3D printed composite parts. The gripper applications, which was actually a complex gripper, which was they were using the casting process, can be 3D printed within some couple of hours in-house without any worry, and then it can match the same strength and same life of the gripper. So these are all few of the examples which talks about how we are. This is one of the examples from a company called Siemens.
The Innovation Center, we're an end-to-end solution provider within Siemens. We're able to take a concept all the way to final implementation, all under one roof. So we saw the capabilities of the Markforged printers, and we saw the finished quality we get from the prints, the strength of the material, And we wanted to have a more industrial printer to be able to fast prototype and also potentially using it as a final tooling. When we first used the Markforged printers, a lot of people thought it would just be used for prototypes. And so there was an initial surprise by our end users that we were actually giving them a 3D printed part that they could actually use in the field or in a repair facility or manufacturing facility as the actual tool.
The major benefit of having the 3D printers in-house is that the time to develop an idea is dramatically shorter. Within a day or 2 days, we can go from an idea that we whiteboarded to a CAD model to a 3D printed part in our hands. So it drives the cycle time down as well.
The Markforged industrial printers act as a digital factory for us. In the past, you would have to make design decisions, do down selections during the design phase. We can now take 3 or 4 different designs, print them out, do the form function test, and then make a decision there which way to go forward. It just allows us to cut costs, and that money is realized back within the business units.
So with the Markforged 3D printer, we get great resolution on the parts. It looks like a real tool that you would buy from a store or something that would be in production.
So if there's an issue with one of the gas turbines out in the field and it has to go down, that means the lights go out or power has to come from somewhere else. So we developed this contoured cutback tool that allows the technicians to make a precise cut exactly where they need to. So this entire contoured cutback tool has been 3D printed. The only off-the-shelf components we had to use were some screws and the actual pneumatic spindle. We were printing this tool as a prototype, but we found that the Markforged carbon fiber composite material is actually robust enough to withstand field use. So we developed 4 kits that are deployed locally.
The Markforged printers have allowed our engineers to be more innovative by encouraging them to fail fast. It allows them to print multiple different designs, make changes to them without having to do that in a design space. And it allows them to get to a final solution quicker, to respond to these rapid prototypes that we have to develop for our business. With the additive manufacturing and the industrial Markforged printers that we're using, the sky's the limit.
So this was one of the perfect examples of coexisting in the production line where 3D printing can be used for the same application, because usually what we used to see was we had to have a high complex metal 3D printer to have the applications for the production. But considering the cost per part of a metal 3D printed part, we would not consider the metal 3D printed part for the production. It was only limited to the R&D prototype. But these particular composite printers from Markforged went past that barrier chain, and then we were able to see numerous of applications where we are using it for the production. All of our printers or all of our customers who are using these particular printers have been utilizing this for their induced production. Here are a few of the tools which were earlier made out from the regular machining of an ABS block or a PC block, or it might be something which is made out of an aluminum or a casted metal part, or it might be something which is made out from an injection molded part. But lot of varieties of those kinds of parts can be replaced, and as we can see, it can be applications which talks about the air tightness, or which can be talking about the leak proof, or which talks even about the EST properties. We have got materials which is EST safe, or we are talking about FR grade. We have got materials which are flame retardant. We have got materials that can be combined with FR plus the fiber material, so that the part can be of a FR grade and also can withstand a huge amount of load, or the part which can be used for such an applications where 3 or 4 metal parts which were manufactured separately and then welded together can now be done as a one single component. So this is where we talk about the, especially in case of institutes where students getting adopted to an industrial exposure, where they are coming to such a development where they get to know, okay, this is not just about printing my prototype or printing my R&D. 3D printers are not just limited to cross verifying my design. If required, I can use the same 3D printer to print my end-use tool, and then that can be used in my production line. So that is where the main benefit of a 3D printer comes in, and Markforged printers have got the full capacity to do those kinds of applications. So here's the printers. I will not go in deep into this. I'll just skip it out. And in the same Markforged, we also do have a metal solution. It follows the same FDM printing process. The difference, one, yes, there is definitely a huge cost difference, because this is the printer which is made dedicatedly for the research institutes and for universities, because you get to operate this metal 3D printer and print parts which are of stainless steel, tool steel, Inconel, copper, all the varieties of metal. And you do not have to just sit back and an operator do the job. No, you can go do your complete hands-on. It's as easy as operating an FDM printer. The best thing, recently we launched a printer called as FX10, which can print with both composites and metal. So it's a one printer which can do both the jobs. We just have to swap our head. So we are just printing from Monday to Tuesday, Monday to Wednesday, we are printing Onyx parts. And then on Thursday, we swap, which takes around a couple of hours of activities. And then I can print my stainless steel on Thursday. And then for the weekend, once again, I can switch back to Onyx. So it's almost as simple as I print both the metals and plastics on the same printer. Yes, there are few additional equipments that are needed for the metal like wash and sinter, but what this advantage gives, you get an advantage of the printer will not stay idle. It's not like, okay, now I don't have any projects in metal, so my printer will be idle for next 1 month. That's never the case. You can always opt to print with the composites or plastics whenever you need to. And then maybe once in a week or once in 2 weeks, you get a project which talks about metal. You can just swap and print a metal part, and then that can be washed and sintered. So these are the different steps. So before I explain to these steps, I'll just play a small video so that it will give you a complete clear view of the metal printing using the Markforged.
Hey everyone, I'm here to talk today about the Markforged Metal X process. It's a simple, safe, and cost-effective method to go from design to functional metal part. There are 3 steps in this process: printing, washing, and then sintering. First, let's start with CAD. You design your part, then export to STL and upload into Eiger. Eiger is a cloud-based slicing and print management system that comes with every Markforged product. This automatically configures your part based on the material and printer you've selected. When your part slices for metal 3D printing, it gets scaled up to account for shrink and deformation in the downstream processes. It then slices your part into discrete layers, identifies overhang features, and builds supports and a raft underneath your part. As we go through printing, washing, and sintering, Eiger will monitor the part's progress along the way. Let's start this print and go to the Metal X. Before starting a print, the machine automatically maps and levels the bed to ensure the first layer goes down well. Your print is built of 2 materials stored in this heated chamber above, one of ceramic release material and one of the metal to be printed. This filament material is metal powder safely suspended within a 2-part plastic binder. It gets heated and extruded onto the build plate where a part is created layer by layer. The release material gets extruded as an interface between the part and its supports, so that once your part comes out of the furnace, it's easy to remove. Unlike other metal 3D printing systems, this process does not require loose metal powder, resulting in a safer and more cost-efficient workflow. 17.4 stainless steel is loaded now. However, with a quick changeover, the system is capable of printing in stainless steels, tool steels, coppers, Inconel, along with several other materials currently in development. Once your part is finished printing, you'll get a notification. At this point, you can go to the printer, remove the part from the build tray, and clear the bed. Now we have what's called a green part. It doesn't really look or feel like metal. However, a large part of it is comprised of metal powder. Next step will be putting it into wash 1 for the debind process. The wash 1 removes the first stage of the binding material. A green part is taken from the printer and placed into the wash basket, which is then lowered into the solvent. Wash times will vary, ranging from a few hours to a few days, depending on the thickest region of your part. After that, it's now called brown part and is ready for sintering. Let's go over to the furnaces. This is Sinter 2, a furnace designed for mid-volume production runs and larger printed parts. Sintering transforms a print from a lightly bound collection of metal powder to a fully finished metal part. First, the temperature ramps slowly to burn away the trace amounts of remaining binding material. Then, temperature ramps closer to the melting point of the material, allowing metal particles to start to fuse together to create a strong metal part. Markforged sintering furnaces use a carbon-free retort to ensure part quality and alloy composition standards are met for our finished pieces. Each run takes about a day and can be monitored remotely using the Eiger software. Once a run is complete, the setter tray full of finished metal pieces can be removed from the furnace. Once removed from the raft, these parts are ready for use. In the furnace, the layer of printed release material between supports and the raft and your printed part remains powderized. This allows the structure to be tacked to the raft to better control shrink and accuracy throughout the process, but also an easy release after sintering. At this stage, your part is fully sintered and ready to be used. It can be post-machined, polished, or otherwise processed as necessary for the final application, but in many uses, the accuracy and strength are good enough as is. It's ready for install. Check out markforged.com for more information about our simple, safe, and cost-effective method of metal additive manufacturing.
Okay, so this was the complete overview of the metal process. So now, as you saw, this is something which all of us can operate. This does not require any sophisticated kind of work environment. We don't have to worry a lot about the health or the safety precautions, because this is something which can be used as a regular FDM grade printer. And then we can definitely utilize this for a lot of our applications and needs. This is just one of the solution what we provide with the metal. Then we also do have printing with metal powders from EOS, which is a German-based company. I'm sure you might have seen a lot of sessions of metal powders. We also have a DED-based concept where powders can be directly sintered and then it can be deposited on the required spot. So we have varieties of applications, and this particular technology of the metal from the Markforged, we have it in our Pune facility. So you can welcome to visit our Pune Philips facility, so that if you want to explore into this kind of applications, so or you can get in touch with us or any of our team members from Philips, where we can work together on the different aspects. So this is just to showcase about how the Markforged has been accepted by almost all the industries, I would say, from the aircraft to automotive to the medical section to majority of the customers who are utilizing this. And as I said, like these are some of the major contributors. And even with regards to the education institutes, not just with the IITs or NITs, we have got institutes like Bannari Amman from Coimbatore who have implemented both of our process in depth, who are providing a complete education on the metal 3D printing, composite 3D printing for almost all the verticals. They are not just concentrated only to the mechanical or to the mechatronics. Even like electronic students are doing their final year project, which has got some amount of 3D printing parts to be done, because they have got an hands-on or 3D printer in their first semester or second semester. So that's the kind of overview which the institutes are now looking into, which is an hybrid concept, because with the current trend of industries, current trend of manufacturing, how it's taking place. So the hybrid approach is always the best approach to learn. So this was all about the Markforged, the composites and the metals. So we're running out of time, but I'll just quickly show you about the liquid and the powder. So I'll not go in depth into it because it's a additional topic which I thought like, okay, I'll just introduce this during our session when we are discussing. So Formlabs is once again a US based company who have got their own proprietary in printing of masked SLA, I would say, where we have the option which is in between the SLA and the DLP concept, which means it utilizes the concept of DLP, which is the complete laser approach, but it also has got a slight amount of SLAs, which makes sure that the quality of the part that comes out, and even they provide a complete turnkey solution from end to end. So the best thing is with regards to the speed, the how fast the particular parts can be printed, and at the same time it can give you a different kind of iterations. This might be something similar to any desktop SLA model that if you might have used, but this is something in a much controlled way rather than having to do the complete maintenance work on daily basis. This is something which gives you the reliability, the confidence, and the repeatability in the products, and the kind of accuracy, the quality. And the best thing is we have got numerous kinds of sensors, numerous controls, and the materials that we use for these particular printers. We have around 30 to 40 different varieties of it, which makes sure that, okay, we have an option of identifying where the error might have happened very easily, and then we can resolve the particular solution. So we have got a smaller size version and a bigger size version of printers in it, so which will give us an idea of printing parts, which is let's say a standard general grade material, or we can also print parts which are of engineering grade materials. We can also print biocompatible materials if that is something of our requirement. We can print parts that can directly be used for surgical guides, We can print parts that can be used for dental dentures. We can print teeth directly, and then that can be used. We can also print parts which can be used for rubber grade like silicon. We also do have an option of printing high temperature materials that can withstand more than 200 degrees of temperature. And some of the engineering grade parts can also be used as an end-use parts for testing and for pilot batch productions. So the liquid technology or the resin technology has evolved a lot. And hello. So these are the different grades of materials. So when we talk about the different grades of materials, so as I was saying, like we have got a general purpose. So these are the regular general category material which we can use for prototyping applications. Whereas the engineering section is actually the main area where we talk about why and how the engineering grade, how it can benefit us, what are the different kinds, because as of today, the materials are actually dictating the applications where it can be used. So we also have got a study which compares an injection molding with our Formlabs liquid printer, wherein we also have run a side-by-side competition, which is the manufacturing 1,000 components. So even though the injection molding has got complete tools, everything ready and set up, we still can print 1,000 parts faster with the addition of 3 to 4 printers together. So that's one of the huge benefits when we are talking about getting the 3D printed parts to the production line. And we have got the powder-based technology, which is the SLS. So this is once again I would not say completely a desktop version of SLS, but this is a very compact SLS rather than you might have seen an SLS or a powder-based solution which takes up an entire room. But this is something which occupies just by the side of your table. This printer can be placed at the side of your table, and it can be operated just like how you operate your desktop printers. But as an end result would be something that will give you the parts as good as an industrial powder SLS. The one of the reasons to showcase this is because these are the kind of improvements that have happened around the industry or the technology where the printers are bought so complex and go so compact so that we can operate it just like our industrial grade printers. Even though we are manufacturing around such a huge complex geometrical parts, we need to manufacture smaller components of very complex geometry of hundreds of quantities. It can be done in just a couple of days, just maybe 1 or 2 days, and then it can be done in-house. So that's one of the major benefit. So these are the varieties of material. We are not just limited to 1 or 2 materials. We have around varieties of material depending upon your application, depending upon your research topics. And the best thing, the Formlabs also provides the open material license. Like for example, with the liquid technology, if you have your own liquid that you want to do research on, so especially for the academics, we have that open option so that you can take the printer and then you can use your own material and do the R&D of it. And with powders, yes, there might be a lot of parameters that has to be done. But if you are somebody who is doing that particular kind of topics, you can definitely explore more even on the powder technology as well. So these are the benefits and advantage. I'm just rushing through because I want to give a lot better time for the Q&A session so that we can discuss more if it is required. Okay, sorry. So with regards to the nylon 12 powder, so this is the regular SLS nylon 12. So when we talk about regular SLS nylon 12, if it is, if we might have heard about the name called it like PA2200, or it might be from the MGF company. So this is something which is similar to the nylon 12 category, whereas this nylon 12 gives us a good tensile strength, but at the same time giving us the flexural and temperature withstanding capacity of the parts. But this particular part is not so good when we are talking about certain areas. At the same time, when we're talking about the nylon 11, these materials have got completely opposite properties of the nylon 12, whereas it has got a very good impact resistance, slight amount of good improvements when it comes to elongation. So, and then we also got the glass field and the carbon fiber field. So the glass field has got its certain advantages, and yes, you can get all of these study materials on our Formlabs website. So you can just go into the Formlabs and then type in SLS materials. So you get to see lot of differences, lot of benefits of which material can give which kind of benefits. And the working process of this printer is also one of the simplest, I would say. So where you, once the part is printed, we have got a completely automated cleaning process where you do not even have to take the parts out from the system. And then once you touch the parts with your bare hands, the parts are completely processed and there is not even a single grain of powder material that comes in contact with you. So that gives us an advantage of completely a safe room working environment. Okay. So sorry, I had to rush through the last sessions because the time, but I think we can have a discussion. If there is any questions that you would like to ask, we can discuss on this particular Q&A questions. And as I said, like, you're always welcome to reach out to us or our visit our facility so that we can see what's any support that is required from our Philips team. We can definitely provide it to you. Thank you. So anybody has any questions related to the topic we discussed, or suppose if anything in your mind, so we can discuss on that. Okay, Naidu sir. So and let us know if anything else need to be done, or we can end the session now. Hello.
Thank you, sir. Dear participants, if anyone have any questions, ask to him. I think no one have any doubts. You may leave now, sir.
Okay, thank you. So thank you, everyone.
Okay, thank you,
So
sir.
I'll reach out if you need any other additional support. Okay, thank you.
Okay, thank you very much.